Hi again, everyone. Welcome back to our course in college algebra. Dr. Tom McNamara here. And in this video, we're going to discuss compound interest. It'll be an important application of exponential functions that we've just been discussing over the last couple of videos. Okay, so let's get right into an example here. So suppose we deposit $300 into an account that pays, let's do this. We're going to, in this example, we're going to say 12% interest. Compounded monthly. How much will we have in 5 years? Okay, so we deposit $300 into an account that pays 12% interest compounded monthly. How much do we have in 5 years? Okay, now, compounded monthly means the interest gets computed each month. Now, you don't get 12% interest each month. What they do is they take the 12% and they divide that by 12. Okay, there's 12 months in a year. So they are spreading the 12% over the 12 months. So that means you are getting 1% interest each month. Okay, now, I'm going to make myself a little table. This side is the months that have gone by, that side is the balance in your bank account. Okay, so you go to the bank, you deposit your $300. You wait 1 month, and then they're going to tabulate interest. So they look at your account, they say, how much is in there? All right, $300. Take 1% of 300, of course it's $3. Very easy to find 1% of something, you just move the decimal 2 spots. You got 1% of that number. Okay, so they are adding on $3. So your balance, after the interest is tabulated, will be $303. Okay. Another month goes by. They look at your account. They say, how much is in there? $303. They add on 1% of this new balance. Okay, so each month you're always getting 1%, but the amount you get is going to vary because it's always 1% of a different balance because your balance is increasing. Okay, so you're going to have that much at the end of 2 months. Once again, the reasoning is they look at your account. They say, all right, there's $303 in there. Take 1% of that. Move the decimal 2 spots and you get 1%. So 1% in this case is $3.03. We add the $3.03 to the existing $303 getting this. Okay, after 3 months, you have the bank look in your account. They say, how much is in there? All right, $306.03. Take 1%. $3.06. Add that on to what's already in the account, and you get this, $309.09. I'm going to do one more just for fun. Okay, 4th month, they say, how much is in the account? $309.09. Add on $3.09 to this amount. Okay, so we have $312.18. Okay, so the amount we're getting every month is changing. Now, I could continue to do the problem like this. it would be extraordinarily tedious, because the problem is asking me how much do we have in this account after 5 years of doing this. Well, 5 years, there's 12 months in a year, we get interest each month, so I would have to do this 60 times, and that would be a huge pain in the butt. Okay, so there's a better way to look at these values. Okay, this is the right way to look at the first month's balance. Why is that? Well, you keep all the $300 plus an additional 1%. Okay, so at each month you have 101% of the balance you had before. All right, so where the heck is my eraser? Okay, so each month you have 101% of the balance that you had at the beginning of the month. I'm going to go grab my eraser. Be right back. And the decimal version of 101% is 1.01. Okay, remember, to convert a percent to a decimal, you move the decimal 2 spots. So if you're talking about 101%, that is 1.01. Okay, so you keep everything you started with plus the additional 1% for 101%. And each of these can be viewed in the same way. Okay, this, you could view it as 303 times 1.01, or 303 times 1.01 squared. Okay, I want you to check these calculations with me on a calculator. Okay. $300 times 1.01 squared. You should get 306.03. Okay, no rounding or anything like that. If you do 300 times 1.01 cubed, you should get $309.09. Now, in this, I do have to round to 2 decimal places. Okay, the smallest amount of money is 1 penny. So when you're dealing with money, your final answer should always be rounded to 2 decimal places. Okay, so the way we would figure out the balance after 5 years is we would take $300 times 1.01 power 60. Okay, let me grab my calculator and we'll go ahead and do that computation. Now, if you have a calculator that looks kind of like this, it's a multi-line display calculator, you can enter this just as it looks. So I'll do 300, first I'll turn it on. 300 times 1.01 power 60 equals. Okay, no rounding, no nothing. So I'm getting $545.01, once again rounded to 2 decimal places. Okay, so when you're dealing with these compound interest problems, don't round until the very end. Okay, so when we're dealing with compound interest, we're dealing with percentage growth, and that lends itself to an exponential function, because we're getting 101% every month. 101%, 101%. And remember, back to grade school, if you want to take percentage of some number, you're multiplying. So you're always multiplying by this factor over and over again. That's why the exponential functions come into play. Okay, now let's look at the components. The 300. The 300 is here because that was our starting balance. Okay? So in the general scheme of things, the number out here will always be your starting balance. The 0.01, that's coming from the fact that we got 12% interest compounded monthly. If we got 12% interest compounded quarterly, it'd be a different number here. The exponent of 60 is the number of interest periods that we've gone through. We get interest every month, so we need to know how many months have gone by. The 5 years isn't really the number we need. Okay, it's not the years that matter in this example, it's the months that matter. So it's 60 months. Okay, so let me write down the general scheme that you need to use for dealing with compound interest problems. Okay, the general formula is this. A, the amount that we end up with in our account, P times 1 plus R over N raised to the NT. And let me go ahead and indicate what the various letters mean. A is the amount we end with, P stands for principal, that's your initial amount, P is your principal or your initial amount, R is the rate, the interest rate, you have to convert that to a decimal when you're doing the computation. And T is time in years, okay? T is time in years. N is number of compoundings per year. Okay, so some typical values for N would be monthly compounding, in which case N would be 12. But it could be different. It could be quarterly compounding, in which case N would be 4. Quarterly means it's compounded every quarter, and there are 4 quarters in a year. It could be daily compounding, in which case N would be 365. Okay? So based on the problem, you will have enough information to figure out these values, and then you can do your computation. Okay, let's do a quick example right here. We deposit, let's make it $750 into an account that pays 4% interest compounded weekly. Okay, so we are depositing $750 into an account that pays 4% interest compounded weekly. How much do we have after, last time I asked about 5 years, let's make it 7 years. Okay, so 4% interest compounded weekly. How much do we have after 7 years? All right, we just follow this scheme. We fill in the appropriate numbers in the right spots. Okay, so A, that's an unknown. We're trying to figure out the amount that we end up with. P, principal, we know how much we're starting with, $750. The 1 is always here, okay, that's always a 1. That's there because you keep everything you had plus an additional percent, so you have more than 100% of what you started with at the end of the next month. Okay, so 0.04, remember that gets converted to a decimal. All right, 0.04 over 52. Okay, so 52 is the number of weeks in 1 year, right? So you have 365 days in a year, 52 weeks in a year, 12 months, 4 quarters. All right, now for the exponent. I would recommend you do it like this. Compute the exponent kind of on the side. Okay, so we're going through 7 years. I have to figure out how many weeks go by in 7 years. So what I do is I take 52 times 7. 52 times 7 is 364. So that's my exponent. Okay, we get interest every week in this scenario. So it's not the number of years that matter, it's the number of weeks that matter. And now I just crunch these numbers here, so 750 times, in this case, if you have a calculator like this, enter it just like it looks. 700 times, open a parenthesis, 1 plus 0.04 divided by 52, close the parenthesis, exponent 364. Okay, so we can just crunch it in one big computation. Here's what I get, $992.24 after the 7 years. Okay? So, memorize this scheme. It's going to come up over and over again in these compound interest problems. Okay? Let's do a couple more examples here. I want to do this. Okay, so let's imagine a scenario here. Let's say kids want to, newlyweds want to become parents, okay? So they're going to have a kid, and they want to be able to contribute to the kid's college fund when the kid grows up. Now bear in mind there's no kid yet, they haven't had the kid, okay? So they're figuring, all right, well, $20,000 will set them up, we could do something with that. So we're going to need $20,000 in, let's go ahead and make it 18 years rather than 20. $20,000 in 18 years. How much should we deposit today into an account that pays, let's go with 5% interest, compounded, what do we want to do? Let's make it compounded quarterly. Okay, so how much should we deposit today into this account that gets 5% interest compounded quarterly? Okay, so let's look at the scheme and fill in everything we know. Okay. Do we know the value of P? And the answer in this case is no, we do not. It said, how much should we deposit? So the starting amount is the unknown. What we know is the ending amount. Okay, so we fill in everything we know. So 20,000 over here, P, that's the unknown, 1 plus. Interest rate is known, 0.05. Number of compoundings a year is known, that's 4. Quarterly compoundings mean 4 compoundings per year. And finally, the exponent is known, because we're going to leave this money in the account for 18 years and let it accumulate interest. We're not going to touch it. We're going to let the balance grow through interest. That's going to happen for 18 years. We get interest 4 times a year. 4 times 18 means we would get interest 72 times. Okay? So what we're going to do is we're going to solve for P. If this equation is true, then it's got to be the case that P equals 20,000 divided by this quantity. Okay? Reason being, I want P by itself. Well, P is multiplied by this number, whatever that number is. I don't know what it is right now. So P times this number gives me 20,000. If I want to work backwards and get to the value of P, I would divide both sides by this quantity. And once we're here, I can enter this just as it looks. 20,000 divide by, left parenthesis, 1 plus 0.05 divided by 4, right parenthesis, exponent 72 equals. So, this is telling me that if I deposit $8,176.88 into this account and I let it grow for those 18 years, then after that time is over, I'll have my $20,000 that I want for the kids' college fund. Okay. So, another application of the compound interest formula. In this case, we knew our target. We knew how much we wanted to end up with. The question was, what do we need to do today to make that happen? Okay, so we filled in all the known quantities and then solved for the one quantity that we didn't know. Okay, so once again, the compound interest formula. Okay, I would recommend committing this formula to memory. It's a really important application of exponential functions. This formula applies whenever we have compounding that is a set number of times per year. There's another formula that we need when we do continuous compounding. Okay, you'll know that you're dealing with a problem that involves continuous compounding because they will say compounded continuously. Okay, that formula is T. That formula is, use this here, A equals P e to the RT. Okay, A equals P e to the RT. It starts out the same. P still stands for principal. R is your interest rate. E is a special number, and if you take calculus, you'll learn why this has to be the formula for continuously compounded interest. Continuously compounded interest is always being compounded. So it's like we take the limit in this formula as n gets bigger and bigger and bigger, and it actually it approaches a definite value, this number E. You can get it on your calculator by pressing the second key and then using the ln key. Okay? So for the rest of this course, you will need a calculator that can deal with exponents. Okay? And if your calculator can deal with exponents, you should have a key that says ln. So for example, on this calculator, okay, my ln key, you can see it right there. Okay, I have a log key, I have an ln key. That's the key you use. I would hit my second key up here, and then ln to get this number. And then you do your exponent here. Notice the slight difference. The r is part of the exponent, not like this. This is for continuous compounding. This is for anything else, like daily, weekly, monthly, quarterly, annually. We would use this. Continuously, we are over here using this. Okay, so two formulas for us to know. The compound interest formula and the one for continuously compounded interest.